Great. So continuing our morning slate of experts in AI for science, telling us about exciting progress in generative modeling, Joey Bose will be telling us about normalizing flow maps.
Yeah, thanks for the kind introduction. It's going to be a hard talk to go after Kirill's great talk, but I'll try my best. So in preparing what to talk about today, I kind of struggled a bit because the audience here is an expert in diffusion models, so I thought more diffusion model stuff. But then I kind of just changed my tune a little bit and decided, well, I want to talk about something that you probably haven't heard about and something that's what I find probably very exciting. And as a result, it's also probably a bit rough around the edges because we're flying the plane as we're building it. But at the same time, I think this is kind of what I'm really passionate about, so let's go straight in. So I want to start off with the same slide that everyone's kind of heard about, what are diffusion models, but hopefully you'll like my animations a bit more. So essentially, we care about dynamical systems. These dynamical systems you're learning this push-forward map where you have this time-dependent generator. And the idea is that you want to kind of learn how to numerically solve this problem, and sampling constitutes like starting from a Gaussian, and then you want to simulate this ODE or SDE dynamics, and hopefully if you do it well enough, and hopefully if you do learning well enough, you'll hit a target distribution that you care about. And also use this opportunity to kind of say my time convention in this talk, where x0 is kind of Gaussian, and x1 is data, which is opposite to the diffusion convention. But sometimes I may screw it up and flip it. But also, this also tells us that when you want to train a diffusion model and a flow-based model, one of the key ingredients that kind of gets overlooked, but we always think about it, is this idea of this interpolant. And this interpolant is what this kind of noising process kind of tells us from starting from a clean image to a pure noise sample. And usually what we want to do is kind of regress some sort of velocity field or underlying transport dynamics with some neural network. So that's all I'm going to say about diffusion and flow-based models, and we're going to go quickly into the next thing, which is this idea, which is I think I've been thinking about a lot more, is what have been the kind of this inflection points of generative models recently, and and what are these things that kind of motivate where we should be heading. And one of the inflection points that's been kind of outside of the realm of diffusion is this idea is moving from pre-training to post-training. This idea where we want to spend a lot more flops, a lot more compute at test time, and you get a lot more kind of bang for your buck when you do so. So you pre-train some model, and then you kind of want to spend a lot more compute at test time, and you can solve a lot more hard problems. And to give you an example, here's a kind of screen grab that I took from Noam Brown a couple of months ago when he was saying that, if you do a lot more test time compute, you can solve a lot of these hard problems and reasoning type problems in math and kind of code and et cetera. And so this idea of test time compute has kind of been this kind of prevailing theme in the past 2 years. And it's also kind of been penetrating into how we think about how we should kind of extend diffusion models, because we've been seeing a lot more of these steering methods, kind of these RL methods for these diffusion models. So clearly, this is a kind of this path that's going forward. But for diffusion models, unlike LLMs, or maybe somewhat similar to LLM, there's an inference tax that you pay. And this inference tax is kind of a lot more severe than people kind of realize. So here's an example. If you're training like a diffusion transformer, here's a stylized example, but what is your approximate cost, right? The approximate cost is you do a forward pass, and then you do the same forward pass for every single integration step in your differential equation that you're simulating. And then if you're doing some sort of reward guidance or reward steering, you're also calling your reward function at every step, right? And if this part is expensive, if you have expensive Oracle reward, your entire cost is very expensive, right? And this inference problem becomes very severe because this is only for one particle. Now, if you want to do something like some particle-based methods where you're simulating multiple particles, this is going to be quickly, it's going to quickly add up. So ideally, what you want to do is kind of, reduce this cost of inference, but still get the benefits of inference. If you really subscribe to this feeling that test time scaling is kind of this new frontier. Now, how are people kind of using this inference process in diffusion models? Typically, we want to solve the reward alignment problem. So yesterday we had a talk about RLHF, so I'm not going to talk about too much of this. But generally, you can frame the RLHF problem as maximizing this reward, and it's clearly this is the terminal reward, so that reward at x1, and you have some KL constraint that kind of constrains your pre-trained model with the model that's being updated. In diffusion and flow-based models, this KL term is a bit problematic because you don't have the KL at the endpoint or the exact likelihood at the endpoint. So sometimes you have to break this down, construct an elbow. But what if you don't want to do this? What if you kind of ignore the fact that this KL term, and we don't want to lower bound this, Are there alternative tools? And this is kind of what this talk is going to kind of push forward, is that if you really want to solve this RLHF problem, like as if it was an LLM, where you do have exact likelihoods, what are our options, and how do we kind of build towards this mindset, where we really want to mirror kind of what's happening in the LLM world a little bit more. So bear with me for a second. If you were to do a reward alignment, what are the current kind of approaches? So Kirill kind of talked about one of them in the previous talk in Feynman-Kautz corrector, so I won't talk about this much, but I'll just give you this cartoon graphic, which is you have a bunch of particles, you simulate them, you do have SMC weights, you resample, and you kind of do this, eventually reward alignment to this tilted distribution, right? But there's also other ways of doing this. You can also do something called diffusion Monte Carlo, where you kind of try to build up this tree, diffusion tree, and can you kind of do this value backup. So the more unrollings you do, you kind of learn how to build the size of these nodes, and the bigger the nodes, the more valuable that state is. And this is kind of really expensive because you have to kind of learn how to build this tree. This is just 2 examples. There's many more examples like guidance, but just to say that the reward at the terminal endpoint is really useful to kind of do all these kind of steering and guidance and tree-based methods. Assuming you had access to likelihood, a lot of these things should be easier. So before I talk about how to do this, maybe you want to ask the question why do I even care about having access to likelihood? If you take a step back, maybe 5-10 years ago in generative models, and you look at all these old papers, everyone reported likelihood as a metric. So here's an example that I took from a paper, and everyone was reporting NLL as a classical metric of performance. And this kind of table kind of brings me a lot of nostalgia because I think about how cute these results were back in the day. So likelihood as by itself is already a metric, but you can also use it for other things, such as likelihood control. So you can use this to kind of very fast steer your generative models, like diffusion models, if you could access that likelihood really quickly. Or you could also kind of do stuff like importance sampling. So you can kind of generate something, and if you had access to a reward, you can kind of resample your generated distribution to kind of follow this Boltzmann distribution that you might have access to. This is kind of a common paradigm in a lot of this AI for science applications, where you have this energy function, you want to generate samples that follow that energy function, and the way you do this, you do importance sampling. But to do that, you need to have exact likelihood under your model. So likelihood gives you a lot of different things. So maybe we want to treat it as more of a first-class citizen. So, you could ask the question, well, if likelihood is so important, why don't we kind of use it already in flow and diffusion-based models? And here's an example of why that could be a bad idea. So when you have a flow, to get the likelihood, you have to kind of solve this augmented ODE, where you have the x1 term and you have the log density term, and you want to evolve this over time. And the second part of this equation is the problematic part, because you have to kind of compute this divergence term. And this divergence is of the vector field at every single time step of integration. Now, this divergence term, you can rewrite this as this trace of this Jacobian. And this trace operation is quite expensive. And we have to compute this trace at every step of integration, right? To give you a flavor for why this is kind of not a great idea is that, the total cost is essentially the number of function evaluations for your integration steps, the cost of evaluating your vector field, and the cost of computing this trace, if you want to get the exact likelihood at the endpoint. Now, you could say, well, trace estimation might not be a bad thing, but actually it can be quite bad if you're working in high dimensions. And this is because if you take the naive estimation of the exact trace, you need d kind of partial derivatives to compute this. But people in the past have used things like trace estimation, stochastic estimation of trace, where you can kind of say, oh, actually, we'll just use some random probes, and we'll get some sort of unbiased estimation of the trace, and where the number of random probes, k, is significantly less than your dimensionality of the problem. But unfortunately, while this is unbiased, you don't often have a handle of the variance of this estimation, right? And you can ask, well, how bad is the variance? Well, the variance actually quite depends on the actual quantity that you're estimating. So if you take the part inside the trace as the matrix A, it turns out the variance is quite tightly related to the Frobenius norm of A. And there's some classical results in the literature that says that if A is semi-definite or positive indefinite, it can be quite bad to estimate this result. So you need a lot more random probes than you would want, right? And there's been a parallel line of work which says, oh, how do we kind of improve trace estimation for generative models? I'm not going to talk about this, but I'll just give you a quick flavor of the results. And the main tool that people do use is that, if you know you're going to compute the trace of something very expensive, you can kind of break it down into two parts. The first part is that I'll break the matrix down into A1 and A2, and I would compute the trace of A1 explicitly, while estimate the trace of A2. And the idea here is to say that if A1 is a SVD, low rank approximation, I can compute this easily. And I will only push the hard part to a stochastic estimation of A2, which might be much more well-behaved. And you can kind of show that if you do this for some types of matrices A, your number of random probes goes from e to the minus 2 to, epsilon to the minus 2 to epsilon to the minus 1 in terms of how many random probes you need. But even this, the fact that we have to do this, may be too annoying for applications where you kind of will get killed by the randomness of the variance. And this is quite the case when you're doing importance sampling. So really, what we want in an ideal world is to kind of have exact likelihood without, all this trace estimation, without all this penalties, and without all this, integration. So, one of the kind of interesting lines of work that's kind of emerged. Yes, sorry.
Quick clarification. I mean, when you say exact likelihood, even if you compute the trace exactly, you're still discretizing.
Yeah. Yeah. Yes, you're absolutely right. So, I mean, exact likelihood up to discretization. One of the motivations earlier was that if you want to kind of bring down the cost of inference, right, one of the things you can also do is bring down the cost of NFEs. And recently there's been this kind of, evolution of work where you do few-step generative models. And they kind of come from the flavor of line of work, if you're familiar with mean flow, flow maps, and kind of distillation approaches, where the idea is that instead of kind of learning the velocity field that kind of transports you, you want to learn the actual jump operator and the jump map, which is a 2-time jump map from any point S to T on this probability flow ODE. And it turns out if you just enforce the condition that, if I jump from S to T, starting from XS and equals XT, and I enforce this properly, you get what's called a flow map. And the way you can kind of reason about this is to say that if S and T get closer and closer together, I recover the velocity field, which is the tangent to the curve. And this velocity field is exactly the same velocity as your flow matching velocity, right? But if I could learn this operator properly, I can kind of take big jumps along the ODE, and I can hit the endpoint with way fewer NFE evaluations, right? And here's one example of how you could parameterize your flow map operator, where you start at XS, then you take this T minus delta jump, and you take the displacement, which is BST, to jump you from one point to the other, right? Now, these flow maps have been kind of studied a little bit for a while, and they kind of hide this implicit velocity field. If you kind of just take the 2 time points and just say they're the same, because you recover the tangent to the curve, they implicitly parameterize the flow matching velocity field. So they have this within them. But of course, you don't have access to them without actually constructing this. The final thing I want to say is that these flow maps, the cool thing about them is that because they have to satisfy jumping along the probability flow ODE, some natural conditions kind of emerge. One of them is the semi-group property of the ODE. So if you take 2 jumps, that's equivalent to taking 1 big jump. So that's the last condition over here. And the first 2 conditions just tells you, if I take 1 small jump and take 1 big jump versus if I take 1 big jump and then 1 small jump, what are the conditions for the ODE that have to kind of be satisfied? These are the Lagrangian, the Eulerian conditions. If you're interested in how these are derived, they're not very hard. You just take partial with respect to time, partial with respect to S with your original jump condition, and you can kind of rewrite all of these from there. But all of this to say that these give you kind of 3 different conditions that have to be satisfied if you want to learn the flow map that corresponds to this kind of black ODE, right? But this also gives you kind of 3 equivalent, pin-style objectives kind of enforce to learning this flow map. And if you kind of optimize all of them, and then if you optimize them to 0 loss, you have essentially one object that can kind of do 1-step sampling, if you will. You start at time 0, jump to time 1, and you have generation. And here's kind of this visual example of what's kind of happening, where you kind of learn how to take this displacement U, which is this big jump from R to T. And that's kind of this what's called the mean flow identity, if you're familiar with the literature. And the mean flow is just an example of a flow map, and this is probably one of the more popular examples of a flow map. Okay, so now I want to kind of revisit some old ideas and kind of apply this modern twist to it. And this modern twist is this idea of kind of taking few-step inference and kind of rebuilding old generative models with these new tools. So one of the old generative models that you may or may not be familiar with is this idea of a classical normalizing flow. So a normalizing flow is essentially invertible generative model, so invertible by construction. Your architecture is invertible. And you have a bunch of invertible layers whose composition is totally invertible. And this is kind of cool because it gives you exact likelihood just through the change of variable formula. And you can write down the exact change of variable and use this as an objective to kind of learn. So this is just maximum likelihood of x1, which is your data. And this has kind of been like, a very classical old way of training these models, but unfortunately, these weren't as scalable as diffusion models and flow matching based models because, the likelihood is kind of hard to train. And also, you have to kind of enforce special classes of architecture to compute this log det Jacobian term. And this has kind of been kind of the state of play where things have kind of stalled before diffusion came upon. Now, the good thing about this model class is that they give you exact likelihood by design, and if you could use this in the same level of fidelity as a diffusion and flow-based model, or flow matching-based model, this would in some sense be preferable because you could do RLHF, you could do a lot of these cool things, right? Unfortunately, these aren't there yet, but what if we could kind of get there? One recent kind of evolution in this kind of flow-based or normalizing flows-based literature is this idea of kind of building autoregressive flows with transformer-based backbones. And this is kind of this way of kind of training this to much higher image fidelity. So all you do is impose a causal ordering of your dimensions, and then you can kind of generate a forward transition and a backward transition analytically. So this is still going to be invertible by design. But you're only learning the mean and the shift operations. And that's kind of really powerful because it lets you kind of still parameterize this mean and alpha parameter with a neural network, like a transformer, but it gives you kind of this scalability that was kind of missing. So yeah.
I'm sorry, if it's invertible, you're restricting the function class. How do you I miss that?
No, it's still invertible, but the reason this is much more scalable is it's like, imagine this is a autoregressive model, but I'm only parameterizing the mean and the alpha, this is the scale and shift. So it's still invertible, it's still an invertible class, but I guess the main benefit of this paper, which was like a couple of years ago from Apple, was that you can kind of pack in a huge causal transformer now, just like as you would do for an LLM, but it's still invertible. So you're not kind of constructing more exotic architectures than you need, just to enforce invertibility. You can get away with something simple as long as you put all the modeling power behind learning this mu and this alpha. And that was kind of the main punchline. So they managed to scale to like text-to-image models, to ImageNet scale, and far beyond, just by using the simple model class, but much more modern recipes. Okay, so this is, I guess, the first interesting part of the talk, which I would say that when we build these modern invertible networks, one of the defining properties is that they should be invertible. But if you look at how these models are trained, what they in effect do is that you essentially add a little bit of Gaussian noise to your data. And in this case, I'm assuming the data is images. And then you kind of learn how to do maximum likelihood over here. And you could say that this step is, in fact, not just engineering trick, but an actual necessity of training. Because if you look at the FID of these models before removing the noise, the FID is quite bad. This is just CFAR. FID of 48 or 50 is quite bad. And what people essentially do is that you train on X sigma, which is a little bit of noise, and then you use this Tweedy's identity to kind of denoise back to X1 or X0, depending on your convention, and that's how you recover clean samples. But if you do this trick to train these normalizing flows, you're kind of breaking this key tenet, which is they're no longer invertible because this is a many-to-one map. And in fact, if you don't do this step, let me show you what happens. What happens is that you don't actually get good FID at all. So here's an example on the rightmost kind of plot over here where you just train on the raw pixel values without adding a little bit of Gaussian noise. And it's almost impossible to train this to the same level of fidelity. And if you do this if I do this Gaussian denoising trick, so the one in the middle, you recover much better FID. So this is kind of this hidden kind of artifact of training these models where, people want to train these models for invertibility reasons, but in practice, they're no longer invertible because you have to kind of employ this trick. Was there a question? No, okay. Okay, so now I want to talk about building what I call normalizing flow maps. And the idea is, what if you can equip a normalizing flow with an interpolant? And it's quite simple. And the simple thing is that imagine we have the same type of interpolant that you have in a diffusion model. So this path that goes from x data to x0, which is pure Gaussian noise. But I want to impose one additional constraint, which is to say that any jump from S to T has to be invertible as well. So exactly invertible. And at the particle level, this means I have particle level consistency. At the distribution level, this means that the push forward distribution, forward and backwards, should be the same. So there's a distribution level consistency. And there's a third aspect, which I'm going to kind of expand upon, which is called time level consistency. And just from these three simple principles, we can kind of rebuild a normalizing flow from scratch and kind of see the benefits of more modern approaches. So what do I mean by this? So here's a flow map that you might have seen earlier, XST. This is the jump operator. To make it invertible between any S and T, the simplest thing you can do is say that I will parameterize the function fst, and I'll say this function class f itself is invertible. Now, you could use an invertible architecture, but the key, I guess, distinction point between a regular normalizing flow is that now this function class f is also taking in time variables s and t. So it's meant to be invertible between s and t. A regular flow would not take s and t. And it's also taking in the spatial variable xs, which is a partially noisy sample. You could do something even more exotic, which is what we call the denoiser, which is to say that I only want to parameterize invertibility at the endpoint, because you might only care about having likelihood at the endpoint. If this is the case, you can say that the function delta st is the invertible component that's being modeled with the neural network. Everything else can be a regular flow map. So this is no longer invertible between any s and t, but it's always going to be invertible from any intermediate jump to time t equals 1. Which means that you have exact likelihood at times t equals 1. Yeah?
Maybe a stupid question. I don't understand the difference between a subscript and inside the after the semicolon.
Yeah, so the semicolon was just to kind of more explicitly say that f is taking in s and t.
As inputs?
Yes.
Okay.
Yeah.
Great. Thank you.
It's the time conditioning, basically.
Thanks.
Yeah. Yeah.
Why don't you think of f of s and t as so a normalizing flow is a composition of small functions,
Yeah.
right? And all of those functions are invertible
Yeah.
too. So any intermediate composition is also invertible. So
Yes.
how is it different from
Yeah, the difference is that invertibility is at the layer level, so each layer. This is invertibility at the path level. So I'm being invertible with respect to an interpolant path. So fst is made of a bunch of layers too, and each one is going to be invertible itself. But I'm also invertible between any jump. I'll explain this a bit more when I get to the time level consistency, because there's a really cool thing that happens, which is that the spatial inverse will equal the time inverse. Yeah, so anyway, these are two different parameterizations you can have, but there's a lot more exotic ones you can think about as well. So let's think about particle level consistency. If my function fst is invertible, I can rewrite all of the same flow map objectives with a NFM and essentially train a normalizing flow between any s and t and between any 0 and 1 without ever constructing the maximum likelihood objective. These are trained purely based on regression using particle level losses, using the standard like L2 regression type objectives. But the benefit here is that at the end of the day, you will get a flow that gives you exact likelihood from any time s and t. So in principle, if this likelihood was very good and the flow was well trained, you have likelihood on the path as well. So you could do a lot more interesting things than you could do with a regular diffusion model because you have access to this very quickly and almost for free. Now you can write the same kind of particle level losses for the denoiser parameterization. The math gets a bit hairier. I mean, algebra gets hairier, not the math. But all this to say that a lot of the flow map objectives kind of automatically port over and have equivalent interpretations to train a normalizing flow type model. So here's an example of what it could look like. So imagine we only want to match the endpoints. So here you have a random pairing of black and blue dots. To give you a bit more intuition why this is not a bad idea, you could assume that some oracle gives you this pairing. Let's say it's an OT pairing, or maybe it's like a rectified flow pairing. And in this case, what a flow or any type of model is trying to do is kind of learn the regression objective from pushing the black dots to the blue dots in one step. If someone gives you this pairing, this is just purely a regression problem, right? So this is just a regression problem of the endpoints. And in fact, you could train a flow this way as well, as a one-step map, where f now is the invertible model. And I want to just map the output of f of x0 to x1. So you can definitely train a flow this way. But unfortunately, this is not as performant because you're kind of missing out on all the intermediate training points. And it will, as a result, overfit a little bit. But this is to say that you can completely train a flow without ever constructing the log dead Jacobian term, which was the problematic part of training with maximum likelihood. Now, I want to talk about kind of this next notion, which is also very interesting, which is this idea of having distributional level consistency. If you give me this interpolant, one thing you can ask for is to say that the time marginals have to match. So the KL of the time marginals PS and the time marginals of the NFM model should kind of match in KL for every S, right? Now, if you impose this kind of objective, this KL is like the forward KL, so this is kind of like an MLE. But this is an MLE tied to an interpolant. So you're constructing the MLE for each point on this path. Now, to do this in practice, you have to kind of operationalize this with a conditional interpolant. So you can say instead of matching the marginals, I can match the conditionals. And this conditional, the first one over here, is the forward transition to noise. And you have this in closed form if you're using Gaussian paths. So really, what this tells us is that we can kind of construct the push forward from any time point S to the endpoint, which is a Gaussian. Because we know what the analytic form of the endpoint is, we can rewrite this as exact likelihood-based objective, but now conditioned on S. So the key trick is that if you start from an intermediate point S, because one endpoint is pinned to a Gaussian, I can use a change of variable from point S to the Gaussian to construct an objective to maximize that. And I can do this for any marginal, or point S on this path, having this conditional interpolant. So this is what we call the single time consistency, where all the times from time S have to be consistent with time 0 for the known forward process as well as your NFM process. Now, based on this, you can kind of write the usual theory, which is to say that the conditional upper bounds the marginal path. You can construct Wasserstein bounds. You can construct show the loss is bounded. A lot of these things, these are kind of straightforward mechanics if you're familiar with stochastic interpolants, flow maps. So I won't go into the theory too much because it's kind of all routine. But one example that I think is kind of cute is to say, why does the conditional bound the marginal? And the simple way to see this is that you can kind of write the joint KL of x0 and xs in two different ways. And because the KL is non-negative, you can kind of then show that it has to always bound the marginal path. So nothing kind of too sophisticated, just to kind of intuitively check that you can train with conditionals, matching conditionals. The other thing you can kind of do is to say, well, instead of having a single time consistency, I want to have consistency at 2 times. This is to say that I want to start from xs, go to xt, start from xt, go to xs, and match the conditional at xs. So instead of starting from 0, I'm already starting from a point xs and going to xt. The picture is a bit easier. Well, let me just go to the picture first. The picture is as the following. Any time jump from S to T has to be consistent, because I can go forward and backward in time, and it should be the same kind of model. And because every point S to T I have exact likelihood, I can now construct this as a KL objective directly. So this is kind of a different type of training method that you cannot do with flow maps, because they don't give you this exact likelihood easily. So this is what I call this idea of going from particle level consistency to kind of this consistency at the distributional level. And you can use this as another training signal to train NFMs. And perhaps the most interesting thing, I don't have a better name for this, so I'll just call this time level consistency. But this is what I think is kind of really, really cool and very new to me and underexplored. Because we have a normalizing flow between our invertible architecture, at optimality, you can say that the time inverse, so switching S and T in your flow map, should equal the spatial inverse, because you have the spatial inverse. It's a regular normalizing flow. I'll stop here for a second, because this is a very kind of confusing concept. But the way you can think about it is that if you define the forward direction of your flow from S to T, and the backward direction of flow from T to S, it says that the log det should be the same if you go forward and backward in time. And it should also say that the Jacobian should cancel each other out, because you should cancel from any jump to S and T and back. Now, why is this kind of like a subtle but interesting point? It's interesting because it lets you do something very weird, and I think it's super weird, which is you can kind of simulate the inverse of a normalizing flow by just switching the time conditioning. If your flow is, or NFM is trained to optimality, then I can recover the spatial inverse by just doing a forward pass by switching the time variables. So why is this practically interesting? If you're training with this kind of autoregressive flow architecture like tar flow, usually one direction of training is really fast, but the sampling is very slow because it's autoregressive. In principle, and we have some evidence for this, is you can kind of simulate a forward pass by switching the time indices from 1 to 0 to 0 to 1, and get the backward pass and generate a sample. And it will be a pretty decent sample. It won't be as good, because it's not always things that don't train to perfection, but you can do this. Okay, so the final part, yeah.
Yeah. So for that result, so how do you put the time conditioning from an architecture point of view? Is it just like adaptive layer norm type stuff?
Yeah.
Because it seems that like when you have this kind of thing, you would like the time to be now more, like in a lot of time when you do diffusion model, you don't really even care about the time. You could even skip the time conditioning. But like here, it seems like it's crucial.
Yeah, it's
like
quite important.
Reverting that, like, do you think that?
So the other part that's kind of important is that you have to enforce these as additional losses.
Right. Okay.
Yeah.
Okay. And I guess that would, okay.
Yeah. So if you enforce this additional losses, it kind of learns how to do this, because this Jacobian at the bottom is kind of forcing this condition as well.
But you don't have to change anything from the from the architecture. You think it's expressive enough to basically
expressive at the level of CFAR and ImageNet.
Okay.
Beyond that, I probably don't know. Yeah.
Sorry, maybe I missed it. Why is it any faster, forward or backwards?
So yeah, let me go to. So usually, the most performant flows these days are these causal autoregressive flows. So when you want to sample from them, it's sequential sampling, just like you would sample from an LLM, right? So you have to slowly generate the sample. But if you had just a regular flow, it's all in parallel, right? So if I want to avoid this sequential sampling bottleneck, what I can do is just switch the time conditioning, and I can have parallel sampling.
Okay.
Yeah. So training is parallel here, but sampling is sequential. So usually you pay the cost in one direction. People pay it in sampling because you sample less. Your training is usually you're bound by training. But if you want to be fast at sampling too, in principle, you can kind of just change the time conditioning. But good question. Yeah, so the final, I guess, the punchline of why this model class could be cool was that I can actually do RLHF the way maybe LLM people intended it. I can now actually construct exact likelihoods. I can do this DPO objective, because I have access to exact likelihood at the endpoint. I can do on-policy RLHF very easily. We found that this on-policy works better for the denoiser than it does for the interpolant objectives, interpolant MLE objectives. But yeah, so RLHF is something that's much more achievable and much more natural. And just to kind of give you a highlight, you can compute the log P1 at the endpoint in two different ways. You can use the forward, or you can use the backward pass. And if both of these are fast, you can kind of pick whichever one is more favorable to you. Okay, so let's kind of just quickly gloss over some empirical results. One of the classic examples that we kind of test these models where likelihood is kind of really important is this idea of Boltzmann generators, where you have essentially this problem of importance sampling. You start from a Gaussian, you generate your P of x, and then you have some energy function, and you want to kind of reweight to your energy of your observables, which is your Boltzmann distribution. So you have U. And you train on a subset of this data set, so you can pre-train a generative model, but you need exact likelihood. So more concretely, usually you train on a data set of like molecules or proteins. And the idea is that you want to kind of construct this importance sampling way where you want to resample using this weight to compute like statistics. And so if you don't have good weights, so this will quickly blow up. So having access to fast likelihood and also good performance is kind of critical here. So some just examples. It turns out if you train with this NFM, it's by far the best model for exact likelihood-based models, for flow-based models, because we found that it's much more kind of scalable to larger proteins than previous normalizing flows. And it's also as scalable, at least on this set of problems, as regular diffusion and flow matching-based solutions. But the benefit is, again, you get fast likelihood. Very quick CFAR results. We can do all the standard stuff, which is guidance, instead of RLHF as well. There's one caveat. The caveat is, and I'll kind of mention this in the limitations, is that when you're training these denoiser-based models, because you're training with only particle level losses, even though the architecture is exactly invertible, it has a tendency to become numerically non-invertible. And that requires a bit more engineering and a bit more kind of tricks to kind of solve. But in principle, we can get it to be kind of invertible and well-behaved. Just to show that we can do RLHF, so this is some CFAR with green frogs. We just kind of RLHF to green frogs. But the final part I think I want to talk about is that this is still kind of this ongoing research program. So we have a lot of things that we don't know, and a lot of things that we wish we had a better idea for. And I want to kind of tell you about some curious phenomena that we've observed and that we don't have a good explanation for yet. But hopefully over time we will come up with more satisfactory answers. Yeah, sorry.
Sorry, when you say RLHF, do you mean literal human feedback or just?
No, I mean like DPO with the reward. Yeah, when I say RLHF, I just mean like DPO. Yeah. One curious phenomena. So here's an example of a scatter plot where each dot corresponds to the importance weight in the case of Boltzmann generators. On the left-hand plot, we have a scatter plot of the importance weights you would get from training with regular maximum likelihood. The middle plot is the importance weights you would get if you were to train with these particle level losses. And on the charts, the bar chart, the energy plots you see here are kind of telling you what the true energy distribution should be. So that's the green curve. The blue curve is the proposal energy, which is what the flow learns. And the red curve is after you resample what the correct energy distribution should be. One of the things we've noticed is that if you train with just particle level losses, you have a lot more weights that are kind of far away and kind of like really far away from what we consider a good resampling area. And this is a common phenomenon that we observe all of the time. And this kind of tells us that the likelihood level representation, if you want to call it that, is less well controlled. But the denoiser gives us the best sample fidelity in terms of just like visual quality. In contrast, if you train with the distributional level consistency objectives, we see that it kind of mirrors this kind of the same shape as MLE, and you can do effective resampling as well. So if you enforce this kind of distribution consistency, it feels it controls this kind of likelihood representation a lot better. Both these model classes are invertible. They both give good samples, but their likelihood performance is quite different. This is kind of this curious phenomena that we've kind of observed.
So when you say MLE, it's like an expectation, and then you say likelihood in your good likelihood is per sample, right?
Yes.
I mean, this is known results that the good sample may not have a good likelihood.
Yes, but I think that
Problem like a Gaussian sample from a Gaussian doesn't have a good likelihood.
so what I kind of wanted to illustrate a bit more with this is to say that these both NFMs over here, the last two plots, they're the same architecture, just trained in a different way. They both give you really good samples, but only one of them will give you good samples and good likelihood. So this is I guess the curious phenomena, which is to say that depending on how you train, even the same model class can kind of give you one benefit, but not both benefits.
But why do you want a good likelihood per sample?
Because I can do on-policy RL. I can answer more.
I mean, a good sample may not have a good likelihood. I mean, this is known, right?
No, but if you had a good sample which also has a good likelihood, you can control it more at test time. This is, I guess, the thesis of on-policy RL.
Good likelihood or true likelihood? I mean, if you do guidance, you need true likelihood.
True likelihood.
Okay.
Yeah,
We can discuss
yeah.
this.
Sure. And I guess this kind of shows up a little bit over here where you want to do resampling. You don't often get good resampling performance if you use just the particle level losses, because it's starting to drop modes because it doesn't actually capture the, I guess, true likelihood as well. And finally, this is something I guess very intriguing is that if you kind of do this round trip business where you start from a Gaussian, generate, and invert the mapping, where do you actually land up? So I'm plotting here in each of these three plots the square norm of x0. So the square norm of the latent, rather. And the black dotted line is where you would expect things to line up. This is the mean of the Gaussian, so the mean of the chi-square distribution. And the green one is where the norm of a standard Gaussian would be. So ideally, you'd want the samples to completely overlap with the green. And we see that in this case, if you kind of just denoise from pure data, you don't actually land back at the typical set. For the MLE case, and in the middle case, if you look at the denoiser objective, it's completely shifted to a completely different area. The scale is completely different. So it's definitely not landing in the same kind of typical set of what a square norm of a Gaussian should be. But if you kind of have this interpolant MLE, we're kind of a bit better. So this is kind of this interesting idea where, where do you map, what is your map actually learning? And it turns out like it's learning quite different things. Even the MLE objective traditionally is not exactly hitting you exactly where the latent norm should be. So I think that's kind of my last slide. And I guess there's three roughly equivalent takeaways here. One of them is that NFMs can be thought of as just invertible flow maps where you architecturally invert them. You can think of them as a generalization of a normalizing float in the traditional sense. Or you can think of this as a new class of generative models that gives you exact likelihood. Both of them are, all three of them are, I think, roughly equivalent depending on your use case. So with that, I'll conclude. Any questions?
I had a maybe basic question. So just to make sure, I mean, these claims are like, if you have like zero test error on all your objectives, then you get like true likelihoods and stuff like this, right? Like this is.
If you have zero test error, you learn the exact flow map.
Like, I mean, like all these notions of like time consistency
Yeah.
and these sort of things, they require having like, you're able to get like good error on all your like generalization terms.
Yeah.
Just in practice, out of curiosity, like what is the actual?
Yeah, so in practice, you can get time consistency if you train for it, but time consistency performance is always is slightly worse than the actual like spatial inverse.
So like so if in practice the time consistency is not that good, then can you actually think of like getting like exact likelihood access?
No, the likelihood is decoupled from time consistency. So you get exact likelihood. Time consistency is used to kind of do this trick where I do the time inverse to get the sample faster, generated sample. But I can get the sample in the regular way, and it will give me exact likelihood as well. Yeah. Sorry, there's two questions over there.
So based on the results, does that suggest that the distributional losses are like just better than the particle level losses?
It depends on what you care about. If you care about just like raw visual quality, then the particle losses are pretty good. They're better than the distributional ones we found. Like if you want to just do like text to image, you will get close to diffusion level quality at that scale. But if you want to do just like RLHF, then it's harder to use that. So yeah, that's why I think it's kind of like this mixed story where what is your actual application? And if you really care about likelihoods like in Boltzmann generators, you would want to use the interpolant MLE objectives. But if you just care about raw visual quality, then the particle level losses are probably better. Yeah. Yes?
I had a quick clarification question. I mean, the exact flow map is invertible, right? Because it's an ODE trajectory?
It's only invertible if it's perfectly learned, right? It's
The exact, I mean like the analytical flow map, okay.
Yeah.
And then for the like RL, there's another way we can get at the Cal term, right? Because if like we have a diffusion process, then we can use like Kirsanov theorem, and then it becomes like some stochastic like optimal control problem. Like how does this approach compare to that family of algorithms?
It's different in the sense that like I have exact likelihood at the endpoint without ever having to compute the SOC objective. It comes baked into the model. The model forward pass will give me the likelihood, which is not something you will get for the SOC-based objectives. I mean, not to say that they're not important or potent. Yes, sorry.
I guess my question is like comparing like a score-based diffusion to these kind of one-shot transport maps. How should we expect kind of error to propagate through the system? Because I know like reading some of the stochastic interpolant frameworks, like if you have L2 epsilon control of your score estimator, you get epsilon control of the KL. That's not true for the ODE path. If your ODE is only epsilon control, that doesn't transfer to KL epsilon control. So how should that kind of play out in this one-shot mapping that's probably not super accurate or 100% accurate?
You have Wasserstein control instead of KL control here, so you can show that if your mapping is under smoothness conditions, you can always control the Wasserstein. But I guess the more finicky point is that more steps doesn't mean you get better samples often. It's often a function of how you train. So usually what we find is that like the 2 or 4 step generation is much better than the 20-step generation. And it's just a function of how you train these flow map-based models. Yeah.
I think you had mentioned that earlier in the talk that part of the problem with the normalizing flows was that the likelihood training wasn't so good. So is your claim that when you do this along the interpolant, the training is better?
Yeah. So I guess one thing I forgot to mention is that in regular normalizing flows, when you do the likelihood training, you add a little bit of Gaussian noise, and then you denoise. Here, that's kind of baked into the interpolant. You never have to do this artificially. So you can get away with just training just based on the interpolant. So I think that's no longer one issue. But I guess the other claim is that you can kind of mix and match objectives. So if you don't want to ever construct the Jacobian determinant term, you would use like a particle level objective. So you can just get away with just pure regression.
But you said that's not as good for the likelihood-based.
If you just want pure likelihood, it's not as good. But if you want sample quality, we will still give you really good samples. So depending on what you care about. I may be out of time, I think.